The next step in our discussion of sequences is to think about what the result will be if we take all the elements of a sequence and add them up. So to do that, I've got this. This is the same sequence that we talked about in the last lecture, only I did make one little addition. I tacked an upper bound onto it. Right, so instead of letting n be everything greater than or equal to 2, I've capped it at 10. So to do this, we could just write out all 9 terms in the sequence, a sub 2, a sub 3, up to a sub 10, put the number into the formula, get a result back out. But that gets tedious pretty fast, even for a relatively small sequence like this one. So we can write this out much more compactly using something called the sigma notation. This expression, it represents the same thing as the one that I've got here. Right, we've got the same formula for the nth term. And what I've done is I've condensed the domain into this initial part here. This symbol, this big symbol in the middle here, that is the Greek letter sigma. It's a capital sigma. Think of it as an S standing for summation, right, with the starting and ending values of the index at the bottom and up here at the top. We refer to this shortened form as the sigma or summation notation, and this longer version here is the expanded form. So before we write this out into its expanded form and try to evaluate it, I want you to think for a minute about what it's saying. The n in the formula here is going to be replaced with the numbers starting at 1 and going up to 5. Now remember what the sigma notation says. It means to add all of those numbers together. So essentially what this is saying here is add up all of the numbers from 1 to 5. That's what the expanded form would look like. 1 plus 2 plus 3 plus 4 plus 5. And that's what you get if you start at 1, count up to 5, and one at a time replace that n with each of those numbers. And again, since this is all numbers, we can't take this a step further, right, and just add all of these up, and the whole thing simplifies to just 15. Now notice that this example has multiple variables. It's got i's and n's. Right, so when you're looking at these expressions, you have to start by being very clear with yourself what the index is. In this case, it's the I, and the n represents the variable ending point of the series. So if I wanted to write out the terms of this series, I would start with I equals 0, then I equals 1, I equals 2. Then I would fall back on ellipses and finish with I equals n. So replacing each of these with numeric values, putting 0 into this expression here gives us 0 over 1, which is 0. You put 1 in there, we get 2 over 2, that's 1. You put 2 in there and we get 4/3 plus ... plus, and now I'm going to put n in there, 2n over n plus 1. Right, and that would be the expanded form of this series. So this series has an interesting property. Try writing out the first 4 or 5 terms of this and see if you can spot what happens as you do that. Okay, so hopefully you notice that there's a whole lot of canceling going on. The interesting part about this is figuring out how the process ends. So to see what's going on, let's write out those first 4 terms. We'll start with a sub 1, a sub 2, probably need a little more room, a sub 2, a sub 3, and a sub 4. So if I put 1 in here, I get 1 over 1 minus 1/2. Then if I put in 2, I get 1/2 minus 1/3. And if I put 3, it's 1/3 minus 1/4. And 4 is 1/4 minus 1/5. So if I add all of the, we'll get to the end part in a minute, right? But if I add all of these together, look at what happens. 1/2 minus 1/2, those go away. 1/3 minus 1/3, 1/4 minus 1/4 minus 1/4, and that process is going to continue. Right? The last term in the last fraction in one term is going to cancel with the first fraction in the next one. All right, so let's see how this ends. And to see how it ends, I'm going to look at the last two terms. That's a sub k minus 1 and a sub k. I know what's going to happen, right? I'm going to get a whole lot of canceling, and there's going to be one term left, and I really want to be clear about which one term that is. Okay, it looks like, based on what I'm seeing here, it's going to be the very last term, right? But let's put some things in here and just confirm that. So a sub k minus 1 is 1, put it over here a little further, 1 over k minus 1 minus 1 over, it's going to be k minus 1 plus 1, which is k. All right, and then I'm going to add that to a sub k. This is a little easier. 1 over k minus 1 over k plus 1. And yeah, look, these two terms cancel. This term would have canceled with the last term over here, and all that's left, well, there's two things that are left, right? There's the first term and the last term. So this whole expression simplifies to just 1 minus 1 over k plus 1. Right? And one thing I want you to notice here, right, is there are no n's in my final answer. Right? All this depends on is the number we choose to put in there for the ending point in the sequence. All right, excuse me, in the series. It's easy to mix those words up, right? The ending point in the series. Okay, this kind of series where all of the middle terms cancel out and all that's left are a first term and a last term is what's called, it's got the name up here in the title, it's what's called a telescoping series, or sometimes you'll see it called a telescoping sum. Now that we've got an idea of how our new sigma notation works, in the next lecture, we're going to take a look at some of its properties.